For series circuits, we used a voltage divider rule to show that the voltage across series resistors divided proportionally to their actual resistor values. We're now going to look at something we call the current divider rule that will help us find current through resistors in a parallel circuit, and it's very similar to our voltage divider rule with a pretty big difference. So for the current divider rule, if we have two parallel resistors of equal value, then the current's going to divide equally through each of those resistors. If the parallel elements have different values, the smaller the resistance, the larger that amount of current through that resistor will be. Now, for parallel elements of different values, the current splits in a ratio that equals the inverse of their resistor values. Remember, for the voltage divider rule, we saw that the voltage across a resistor to the total voltage was directly proportional to the resistor value to the overall resistance. It's actually backwards for the current divider rule, where the current through a resistor is proportional to the total current as the total resistance is to that one resistor of that branch. Okay, I'll show you what I mean. It's inversely proportional is what it is. Okay, so here, let's look at our first circuit on the left. We have three parallel resistors, a 10 ohm, a 100 ohm, and a 1 kilo ohm resistor here. The greatest amount of current of the 9 amps is going to go through the 10 ohm resistor, and the smallest amount of current from that 9 amp source is going through the 1K, with the 100K being somewhere right there in the middle. So how do we find the current divider rule? Well, basically what we're saying is Ix is to the total current of the circuit, as is the total resistance to that one resistance, or Rx. Okay, so what we need to do is find RT first. Okay, and in this case, that's 1 over 1 over 10 plus 1 over 100 plus 1 over 1,000. The total resistance should be about what? If you said less than 10, you are right. So I get about 9.01 ohms or something close to that. So what we're doing is we're saying, and if I multiply in my relationship equation here, if I multiply both sides by IT, I get that I sub x is equal to RT over Rx times IT. All right, so that means that the current I1 would be the 9.01 over 10 times IT, which is my 9 amps. Okay, so about 90% of my current from the source or from that node should go through this particular resistor. So I get 8.11 amperes. And so definitely the biggest portion of current is going through the 10 ohm resistor, like I said. Okay, so let's look at I2. So I2 should be RT over R2 times that total current coming in. So we've got 9.01, that's RT, over 100. So basically 9/100ths of the current should be going through there. Or about 0.81 amps there. And then for I3, let me draw that in, 0.81 amps here. And then for I3, again, RT over R3 times IT. So you've got the same RT divided by 1,000 this time, times the 9 amps, or 0.08 amperes, or 80 milliamps. So when you add this up, 8.11 plus 0.81 plus 0.08, we get 9. Okay, so that's the current divider rule. So let's apply this again to our circuit. Now actually, let's talk about the ratio here before we move on from this circuit. The 10 ohm resistor saw about 8 amps of current through there. So 100 ohms, which is 10 times our 10 ohm resistor, saw what? A tenth of that same current. And the 1000 ohm resistor, which is 100 times the 10 ohm resistor, saw about 100th of that resistance. So keep that in mind as we're working through this. Okay, so let's look at our next circuit here. So this time we're given I2 and we're given the 3 ohms here, and we know all the resistor values. So I'm going to find RT here first, which is 1 over 1/6 plus 1/3 plus 1 over 1. So our total resistance should be less than 1, right? 6. So we've got about 0.67 ohms as our resistance. Okay, so I2 should be RT over R2 times the total current, but we're looking for the total current this time. So if we solve for that, IT would be R2 over RT times I2. So we just did some algebra here, and it's not necessary that you do that with me in this case, but if you have some questions about that, let me know. So we did some algebra here. So R2 was 3 ohms over the 0.67 ohms RT, and we have 2 milliamps there. So if that's the case, that means we should have 9 milliamps total. So let me draw that in right here. So 9 milliamps here. 2 of them through the 3 ohm resistor, right? So let's go ahead and use our voltage divider, current divider, sorry. Let's use our current divider rule to calculate I1, which is RT over R1 times IT. Now that we know what our total current is, so we've got 0.67 over 6 times 9 milliamps. Or about 1 milliamp there. So I'm going to draw that in. Now notice something. I want to draw this in because I want you to notice that our 3 ohm resistor has 2 milliamps of current through it. Our 6 ohm resistor, which is twice R2, has half the current through it, right? So if that's the case, let's look at that 1 ohm resistor. Okay, so we have through a 3 ohm resistor we have 2 milliamps. If we have 1/3 of the resistance, how much current should we have through that resistor as R3? Well, if we have 1/3 of the resistance, we should have 3 times the current, 6 milliamps. Well, let's work it out and see if that's true. So I3 would be RT over R3 times IT. So we have 0.67 over 1 times 9 milliamps, or 2/3 of 9 milliamps, which is, of course, 6 milliamps. So that works out that way. And we didn't even really need to do a lot of the calculations because, like I said, if you have a 3 ohm resistor showing that you have 2 milliamps through there, a third of that resistance will have 3 times the current, and twice the resistance will have half the current. So once you start seeing these relationships, I think this will get a whole lot easier for you in doing these calculations. Okay, so let's work through a couple more problems with the current divider rule so you can see how this works. So here we have 12 milliamps of current through a current divider circuit of 3 resistors. So I'm going to start by finding RT. So we have a 1K plus a 10K and a 22K. Now I'm just writing this as K. If you leave out the K, as long as they're all in kiloohms, that's fine. Just remember that your answer at the end has to be in kiloohms, or you'll have the wrong current there. So I get 873.02 ohms of current. So if you did this without the K in there, you would get 0.873, which is 873 ohms. All right, so current divider rule, I1 would be RT over R1 times the total current coming in. So we've got 873.02 ohms divided by 1,000 ohms, times the 12 milliamps coming in. So that means 10.48 milliamps is what we should see through R1. We're going to do I2 the same way, maybe underneath here. So we've got, again, 873.02 ohms is RT over 10K times that same 12 milliamps coming in. Which should be just a tenth of this. Or 1.05 milliamps. So it's about a tenth of the current that we saw in branch 1. And then for I3, we have the same RT, this time over 22K, which should be whatever's left over when we take out the 10.5 and the 1.05 from the 12 milliamps, but we're going to go ahead and calculate that. And I get about 0.48 milliamps there. So just a little bit of current there. Now, remember the 12 milliamps should equal the 10.48 plus 1.05 plus 0.48 . And it's very close. It's like 12.01, probably because of my rounding. What is another way we could check? Well, we could find the voltage drops across each of our resistors, because what would V1 be? That would be 10.48 milliamps times 1K ohm of resistance, or 10.48 volts, right? What would V2 be? Well, 1.05 milliamps times 10,000 ohms, or about 10.5 volts, okay? So about the same thing, and if we multiplied the 22K times the 0.48, again, we should get right at about 10.5 volts. Again, there are some rounding issues here, but you should get the same voltage drop across each. we should be able to multiply, take that voltage drop and divide by RT and get 12 milliamps as well. So there are several ways of checking behind and making sure that we did this right. Now, I'm going to show you a special case for the current divider rule. And like I said, when there's a special case, it means that certain conditions have to be true in order for you to use this special current divider rule I'm going to show you. And this is going to be for 2 branches only. Okay, so if you only have 2 branches, you can use this particular current divider rule that might save you a little bit of time. Okay, so in this case, if we want to find I1, what we're going to do is take R2, that's right, we're looking for I1, but we're going to take I2 on the top of this fraction and divide by R1 plus R2, and then multiply by the total current coming in. Again, just a special case for 2 branches only, but it's a little bit quicker in that you don't have to find RT first. So that would be 8K over 2K plus 8K times our 20 milliamps. So basically what we find is that 80% of that current, or 8K over 10K, should be coming through the 2K ohm resistor, or about 16 milliamps. If you want to check, remember the other current divider rule should also apply, where you have RT over R1 times IT, and RT is what? 1 over 2K plus 1 over 8K. I'm going to calculate that real fast. So we've got 1.6K here. So 1.6K over 2K times 20 milliamps should also equal 16. Okay, so that checks out. So using our quick rule again, how would we find I2? Well, that would be R1 over R1 plus R2 times your total current coming in. So that means 2K out of 10, or 20% of that current, should be the current through I2. So we should have 4 milliamps here, 16 milliamps here, coming from 20. And of course they will go right back together at the end. And that's what we'll see.